Alright, let's continue our discussion of the periodic table and quantum chemistry. In the last video, I finished off by saying that the energy levels of electronic excitation or relaxation correspond to the rows in the periodic table. I'm going to break down the periodic table into four specific regions, and then I'll show you how the row ultimately is highlighted to the specific energy level of the element. But before I do that, I do need to emphasize another aspect of the quantum numbers. I did mention to you that the wave function describing the interaction of the electron and the nucleus can be subdivided into uh, three individual wave functions themselves. And when you look at the ones that relate the angle at which the electron is positioned with respect to the origin axis of the nucleus, you develop a new set of equations that ultimately spit out a set of quantum numbers. Now, the quantum numbers that I'm referring to have a name of their own. We refer to them as orbitals. Now, the orbitals, as you can see, have a 3D picture of how the electron is interacting and moving about the nucleus in equation form and in wave form as well. So these orbitals tell you a little bit about the shape of this interaction. The first shape is what we call an s orbital, and it's completely spherical. The second shape is called p orbitals, and it looks kind of like a peanut. And the peanut could either be going left and right, top and bottom, or in and out. And all three of those possibilities are likely to happen because, of the shape of the p orbital. Then you have d orbitals, for which there's 5 possibilities, and then there's f orbitals, for which there is 7 possibilities. And the one thing to look and notice is that going from s to p to d to f orbital, the number of possibilities increases in order of odd numbers. So number 1 for the s orbitals, only 1 possibility. 3 possibilities for the p orbitals, number 5 for the d orbitals, and only 7 possibilities for the f orbitals. Now, in terms of shapes, I probably am more concerned for you remembering how the s orbital and the p orbitals look like. In due time, you'll be asked to, you know, remember the d orbitals as well, maybe in the next chemistry series, or perhaps a few chemistry series down the road. But s orbitals and p orbitals is what I will consider that you remember how they look, and be able to draw them as well. All right, now the thing about them is that in conjunction with the energy level, we're gonna start seeing how the periodic table um, kind of can be described with those specific quantum numbers. There's one quantum number left over though that needs to be mentioned, and this is the spin quantum number. Now, the spin quantum number ultimately shows that the emission of light from the different excited elements could be ultimately deconstructed into a set of duets. Now, this could only happen if you actually place the element that was being excited and was emitting light in the presence of a fairly strong magnetic field. And what will happen was that the original emission line obtained in the absence of the magnetic field will split up into a higher and a lower energy levels. And that was true for all of the emission lights. And if you compare it to where the original source of light was present, there was actually a plus or minus amount of energy from the original point to the higher and lower point for each one of these individual rays of light. And the only way to explain this particular intricate experimental observation was that because there's magnetic fields, there has to be a magnetic interaction that is also being affected by the magnetic field applied to the element. And one of the ideas came up that, well, the electron has a charge of its own, and we do know that anytime that a charged particle is moving, the movement of the charged particle creates a magnetic field. So here came the proposition that the electrons must be spinning on their own axis, kind of like the Earth spins on its own axis as well. And the spinning motion itself creates the magnetic field, which is the reason why you have, the energy of the emitted light, going up in some amount or going down in some amount, because there's an equal likelihood that the electron could be spinning up or counterclockwise, or it could be spinning down or clockwise in this case, right? Now, ultimately, what this means is that the electron has two possibilities. Either it spins up or spins down, which means that it either creates a magnetic field that goes along with the magnetic field of the instrument or against it. And that explains why you have an increasing energy or decreasing energy. All right, so now altogether, we're going to see what this tells us with the periodic table. The spin number is associated with something known as the Pauli exclusion principle, which says that not two electrons could ever have the same for quantum numbers, or that not more than two electrons could ever be present in the same energy level. All right, so let's take a look at the periodic table, and this time I'm going to highlight 4 regions in it. Notice that groups 1 and 2 are highlighted, in red. This is called the S block. The transition metals are highlighted in yellow, and this is known as the D block. All of the elements here on the right side are known as the P block, and the elements down here are known as the F block. Now, the energy level itself, the number of the energy level is associated with the row number. Specifically, for the S block and the P block, the row number is literally the value of the energy level. For the D block, however, the value of the energy level is the row number minus 1 in which the element is located. And for the F block, the value of the energy level is the row number minus 2. And the one thing to be kept in mind is that lanthanum starts at row 6. Actinium starts at row 7. Alright, so technically that's where they start, and they fall in between the S block and the D block. But if you were to place all of the F block in between, the periodic table will be rather large. Okay, so in the next video, I am going to start the process of depicting how to derive the electron configuration of neutral atoms. So I'll see you then.